Okay, we said one way to prepare anhydrides is reacting two carboxylic acids, and the shortcut I gave you is circle the part that's lost. Obviously that will form water, which is this, and then click the rest of the structure together. You're gonna get this, because carrying from here is gonna be that bond joined to the other structure. That's by heating two carboxylic acid, two equivalents of carboxylic acids. The mechanism was described in the lecture. So one can also make a ring. So it's gonna end up being a 6-membered ring, including the oxygen. Okay, that's a 6-membered ring. So you use the same shortcut. In this case, the easiest way again is to coil the ring and then use the same shortcut. This is lost as water, and then this oxygen will be bonded to that carbonyl to close it. Of course, there's another carbonyl here, so this oxygen will be bonded to that carbonyl. You close the ring. That's the shortcut again for making this anhydride, cyclic anhydride. Okay, and then the other one was acylation, where you use an acetate as a nucleophile to attack an acyl halide. Okay, so generally if you have an acyl halide and you have an acetate, so you expect this to attack the carbonyl, this to leave, so you'll get your anhydride, and this is the best one because Cl is a good leaving group. This is a nucleophile here, a preferable nucleophile, so you get your anhydride, which is specifically what was shown here. You use the acetate, attack, this falls off, you get this anhydride. And you're not losing water, I corrected that. You're losing Cl minus and sodium, so you get sodium chloride. I'm just giving you a review of what we did last. So now we proceed from here. Okay, one can react anhydrides with nucleophiles. The first nucleophiles we are looking at is an amine. Specifically, this is ammonia. Okay, so we're going to do substitution here. So when the ammonia attacks the carbonyl, this whole thing will fall off. This is a very summarized reaction. So what you get is, I'm not showing the complete mechanism, I'm just carrying the mechanism. So you'll get that, and this piece that falls off, the bond, the two electrons that make the bond go to the oxygen. Okay, so you make an acetate on the other side. Now you realize that this can accept a proton. So if I edit here and say let me show two hydrogens and the third one exposed, so this can be used as a base to take out that hydrogen and neutralize the nitrogen, because like I keep telling you, the two organic salts will not want to stay charged. So this will rather take out the extra hydrogen that came with ammonia, neutralizing the nitrogen. You're gonna get a lone pair there. You end up with what's called an amide. And like I told you, amides have amide bonds, and that's what you see in peptides or proteins or DNA. Okay, so as this accepts the proton, it's gonna give you a carboxylic acid. So anhydrides are not very stable. They can react through a substitution reaction, because specifically this is SN2, because you're attacking with a nucleophile and you have a leaving group. Okay, this would have been the leaving group. This is what's formed after the nucleophile attacks. Okay, so alcohol and water will react in the same way as ammonia, which means you can put water here, you can put alcohol here, and the leaving group is a carboxylate anion, which will get protonated to form the acid. So that's the carboxylate anion. This is the carboxylate anion, which gets protonated to give you the carboxylic acid. Okay, so let's see. Amides. This is the general structure of an amide functional group. Of course, we always say that is the least reactive of the carbonyl containing structures. It's least reactive. It's less reactive compared to carboxylic acid. Of course, we know carboxylic acid is less reactive than an ester, and an ester is less reactive than anhydride. Anhydride is less reactive than acyl hydride. Okay, so in terms of reactivity, amides are less reactive than carboxylic acid less reactive than esters less reactive than anhydride less reactive than acyl halides. So this is called a primary amide. Why? Because you have no R group. You have two hydrogens here. So let's see. Compare this to ammonia. So now you have NH2s, right? So this whole thing could be taken to be the R. So this is called a primary amide. Okay. Let's see if they have secondary amides. No. So let me show you how a secondary amide will look like. Secondary amide will be an R group. This time one of the hydrogens replaced by another R group. That's secondary because again the nitrogen is substituted twice. Two hydrogens are missing compared to ammonia. And then there is tertiary amide where there's no hydrogens on the carbonyl or the nitrogen. So this time you have the nitrogen completely substituted. There's no hydrogen. So that's a tertiary amide. Okay, because you have a lone pair on the nitrogen, you expect it to undergo resonances. You remember what we said, amides are less reactive, and this explains why. Because this carbon should be partially positive to be attacked by a nucleophile, right? But you see there's a lone pair that's killing this positive character, so you barely have a partial positive charge. You barely have a partial positive charge on this carbon because the lone pair is neutralizing it. Anyway, if you do resonances in blue arrow, you're gonna get this. Here you have two lone pairs. After giving it the two electrons that made the bond, you get three lone pairs. And you get a double bond, the nitrogen becomes positively charged. So these are resonance contributing structures. Now, as far as rotation goes, the resonance structure here has a double bond character. So you know that double bonds are rigid. They are not like sigma bond. They are not like single bonds. With a single bond you can rotate, but with a double bond you cannot. And because of resonance, you have a hybrid pi bond here. So this cannot be rotated, which means this will not be rotated because you keep shifting in between single bond and pi bond. You have a hybrid of a pi bond character. Okay. which behaves similar to the CC double bond, which cannot be rotated. So amide bonds are rigid and don't rotate. Okay, so you have, in terms of intermolecular forces, because you have hydrogens bonded to the nitrogen, one can expect to have hydrogen bonding between one amide group and another one, right? And that helps to even hold peptides together or proteins together. So nitrogen is partially negative, the hydrogen is partially positive because nitrogen is more electronegative than hydrogen. You expect that an partially negative oxygen of another amide will be attracted to the partially positive hydrogen of the other amide, and in between them you're gonna get hydrogen bonding. Like I said, this holds proteins together, DNAs in biochemistry, and so forth and so forth. Now for small amides, because of the presence of hydrogen bonding, you'll find that the small amides are water soluble, because we said like dissolves like. Okay, they are water soluble because, again, you would expect the oxygen of water to be hydrogen bonded to the hydrogen of the amide. Okay, so you have hydrogen bonding. The hydrogen bonding helps to dissolve small amides in water, but not large ones. So how do we make amides? So for primary amides, what we can do is condensation reaction by heating. Alright, so again, I'll always give you the shortcut. Uh, that's your ammonia, NH3. You lose H and OH, which is gonna be lost as water. Click the NH2 to the carbonyl. Okay, click the NH2 to the carbonyl. You get your amide. You get your amide. Okay, and this is primary amide because compared to ammonia, you're missing one hydrogen which was substituted by carbonyl R group. So it's primary. In, I can call this whole thing to the left as an R, but I know in there's a carbonyl, so it makes it a primary amide. Okay, what is lost in the process? This reaction is not very easy because carboxylic acids are not reactive. So I described to you secondary amides. Always compare with ammonia. This nitrogen only has one hydrogen, two hydrogens are missing, so it's secondary amide. Or rather, you could take it as R, R, H. We know this contains a carbonyl, so it's an amide. You're seeing two substituents, so it's secondary. And of course, this will be tertiary. Okay, note that the nitrogen in tertiary amide no longer has a hydrogen uh, donor. Okay, the nitrogen no longer has a nitrogen. Like here, there's no NH, so you don't expect hydrogen bonding. Okay, no hydrogen bonding. All the hydrogens that were in the primary amide, these have been replaced by R group. There's no hydrogen, so there's no hydrogen bonding in tertiary amides. In secondary amide, you can do hydrogen bonding right here with another amide or with water. You can do H bonding. Similarly, you can do H bonding with primary amides as described earlier. Okay, so what are the reactions of primary amides that will lead to formation of secondary amides or tertiary amides. So this reaction is called N-alkylation, nitrogen alkylation, meaning you are adding an alkyl group. You're adding an alkyl group, alkylation, adding an alkyl group. This happens by SN2 mechanism. It's a nucleophilic substitution type of a reaction. You are using a lone pair of nitrogen to attack an alkyl group of the alkyl halide. So let's say you have this amide, and then you have, let's say, a methyl chloride. So one would attack the methyl. Why? Because its carbon is partially positive because of dipole moments, and then this bond breaks towards the chlorine. Okay, so it's an SN2. You can push the arrow up like was done here or down, it doesn't matter. It's a concerted reaction, is SN2. So what do you get? Your CH3 is there. You're gonna get your NH2 with the CH3 now added. The nitrogen will be partially positive. Remember that Cl fell off, right? So organic molecules don't like being charged. So that nitrogen has to lose the extra bond. By losing the hydrogen, the bond is used to neutralize the positive charge, and that's how you get your product, where the CH3s will be these two R's. For example, you are left with one hydrogen on the nitrogen, which is this. Now when the Cl takes out the hydrogen, what do you get? HCl. As always, I'll always give you the shortcut. So if you have at least a hydrogen on your amide, okay, and we are adding an alkyl halide. So the shortcut is to know that you're gonna lose a small molecule, usually it's water or HCl. So whatever I've circled will be lost as HCl, and then the rest clicked together. That is a shortcut that you can always use to get the product. So now your CH3 is bound. That's your R group, which is these two guys. Small molecule here lost. Alright, exam shortcut. So you will have prepared your primary amide. You will have prepared your secondary amide from your primary amide. Again, this is primary because the nitrogen is substituted with one carbon containing group. Here this is secondary because the nitrogen is substituted with two carbon substituent groups. Okay, as like esters, amides can be broken down by the help of water. So again, you're simply gonna lose the NH2 and it's gonna be replaced by OH. Let's go with our shortcut. So the shortcut that you would use in this hydrolysis is to use the primary amide with water, because you're using water to break it down. Then we're gonna lose the NH2 and the hydrogen of water, because we're using H2O to break the amide, and then click the rest of the structure. So I think OH replaces NH2, so I would draw what's joint. that bond is bonded to OH. So whatever is circled, NH2 plus H, will be lost as ammonia. So that will be the shortcut of hydrolysis of amides to carboxylic acids. So you will have converted your amide to carboxylic acid. Like esters, amides can be reduced, okay, and you have to use this strong reducing agent. We talked about this before. We said that lithium ammonium hydride reduces esters to primary alcohols. Here it's gonna reduce amides to primary amines. This is a primary amine because you have one R group to the nitrogen. There's no carbonyl, so it's not an amide, it's an amine. This whole group is the R group, so it's primary. There's only one R group to the nitrogen, primary amine. So basically, reduction is removal of oxygen, right? Or addition of hydrogens. So here, this whole oxygen is lost. In its place, we are adding two hydrogens. So you're losing oxygen, you're adding hydrogens, two evidences of reduction. So it doesn't matter. So if you have benzamide and you do lithium ammonium hydride, you'll expect that where the oxygen was, two hydrogens will be put on there to keep the 4 bonds around the carbon. That's still a primary amine. Okay, so what if you have this amide? If you have this amide and you're doing lithium ammonium hydride, you're not gonna end up with a primary amine, you end up with tertiary amine, because simply put, just where the oxygen is, put two hydrides. You see, now the nitrogen is bound to a CH2, not as carbonyl. Anyway, this is a tertiary amine. What I want you to realize is if you start with tertiary amide, and you're reducing, you get tertiary amine. If you start with primary amide, you're reducing it, you get primary amine. If you start with secondary amide, let's do a secondary amide here, you're reducing it with lithium ammonium hydride, you're gonna end up with, okay, the hydrogens are there, I don't need to show them, you're gonna end up with secondary amine. So secondary amides will be reduced to secondary amines, primary amides will be reduced to primary amine, primary amide will be reduced to primary amine, tertiary amide will be reduced to tertiary amine. See, you have 3 R groups. Okay, so switching gears, alpha hydrogens of esters. Now, to remind you what alpha hydrogens are, in ketones we said any carbon bound to the carbon is called alpha carbon, and that alpha carbon can have hydrogens. Those hydrogens will be called alpha hydrogens. And we said if you have a base, that one of the alpha hydrogens can be taken out, okay, you end up with a carbanion. For example, this carbanion, which can be used as a nucleophile to do aldo reaction. Okay, this can be used in aldo reaction. So in esters, we do what we call Klein-Sen condensation. So similar to aldehydes and ketones, the alpha hydrogens of esters and other acid derivatives are weakly acidic and can be removed by strong bases like I did here, okay, such as alkoxide, for example, methoxide. Any strong base will remove the alpha hydrogens. The products are alpha ketoesters. Instead of aldo products, we get alpha ketoesters. This reaction will not work with an acid, as the base will react with the more acidic proton of the acid rather than the alpha atom. So you always need strong bases. You must use a strong base, not an acid. So let's describe what's happening. Again, you have an alpha carbon, which is a carbon bound to the carbonyl. These are alpha hydrogens because they are sitting on alpha carbons. So if you have a strong base, let's for example say OCH3 to represent O a negative, which is an alkoxide, which is a strong base. This strong base can take out one of the alpha hydrogen. The two electrons that are bound to that hydrogen are donated to the alpha carbon. So you get what we call a carbanion. The carbanion can do resonances. You make a double bond here, the pi bond opens up towards the oxygen. Okay, you have two lone pairs. So now you end up with three lone pairs. This lone pair can come back in to make a pi bond, and then this pi bond opens up to go back to where you began. So this is the carbanion form. This is the enolate form of the ester. Okay. The resulting enolate is nucleophilic. You can use it as a nucleophile to attack a carbonyl of another compound. What I mean is you can use your enolate, use one of the lone pairs from up there, okay, make a double bond. This opens up and can be used to attack another carbonyl. Okay, you can attack another carbonyl and this will open up. Anyway, that's what this is saying. Not very clear, but next slide you'll see what I mean. So you use the enolate to make you use the lone pair to make a double bond. When this pi bond opens up, it can be used to attack another carbonyl of another molecule where the carbonyl will open up. So it can be used as a nucleophile. Okay. Now, for purposes of this class, I will not use the enolate to show this nucleophile character. Instead, I'll use the allow me to use this carbanion, which can form an enolate. So you can use the carbanion to attack, use this as a nucleophile to attack another carbonyl of another molecule, and this can open up. So that's what's shown on this slide. This reaction that I'm trying to introduce is called a Klein-Sen reaction, where you're joining two pieces of an ester using the carbanion as a nucleophile. Remember, the carbanion could have as well been the enolate, but I'm preferring to use the carbanion as a nucleophile, not the enolate. So let's start from up here. You start with an ester. This is the alpha carbon, not this, okay, not that one. This is the alpha carbon. So you can use your alkoxide, which we said is a strong base. In this case, you have the ethoxide to take out one of the alpha hydrogens. You make a negative charge right there. That gives you the carbanion. You see how you had sodium here from your sodium ethoxide. This is sodium ethoxide. So the sodium is just a spectator ion which comes back to hang around the negative charge of the carbanion, stabilizing it. When OET minus accepts the proton, you get ethanol. Okay. Now we use our carbanion that we formed up there down here. So we are using it as a nucleophile. We use it to attack the second ester molecule. So the first ester molecule is used to make the carbanion. The second ester molecule will play the role of an electrophile, similar to what we did in aldol condensation in the chapter of aldehydes and ketones. So you use the lone pair of the alpha carbon of the carbanion to attack the carbonyl of the second ester molecule. When you attack it, the pi bond always gives way, but now you know this is how it happens. This carbon is sp2. You end up with sp3 carbon. Okay, and that is a tetrahedral intermediate. Now let's track what went where. So let's assume that this carbanion is gonna be in red. All right, let's assume this one is in red. And for purposes of teaching, let me just label this with an asterisk. So that carbon was clicked to this carbon. I'm gonna give it 2 asterisks. So which means this is the carbon that was attacked. How do I know that? The oxygen is now negatively charged. After the carbonyl opens up, you get 3 lone pairs which is negatively charged. So this carbon here in the middle, this sp3 carbon there in the middle, is this one. And then the carbon of the carbanion that did the attacking is gonna be this one. So this blue bond, let me take the blue bond, this blue arrow, okay, that blue arrow is this bond in between. So you joined the red piece to this second molecule. So this would have been your red piece right there if you had to track it. That's your red piece that attacked the other carbonyl. Okay, so you've clicked the 2 molecules together. This and this are clicked together. Okay, you get a tetrahedral intermediate. So O minus will come back, make a carbonyl, and then this OET falls off. You would have ended up with this structure. Okay, so there's something missing here. That should be a methyl group. So this piece right there is this piece after OET leaves, and then if I'm to show you the other piece, this piece right here is this piece right here, which is just this piece, and then OET left, or CH2CH3 left as a leaving group. Okay, now what was formed here, there's a methyl group, what was formed here can still react with the alpha hydrogen. There's an alpha hydrogen right there, so you can use it as a strong base again to take out the alpha hydrogen to make a negative charge. So the methyl group is there, the lone pair is there with the negative charge, so you get ethanol. But because you don't want the negative charge, one can finish the reaction by adding an acid, where this lone pair will just accept the hydrogen, okay, and then you're left with a neutral molecule, which is still this molecule. Okay, I'm just showing you these steps here, just the side reactions that keep going until you stop the reaction by adding an acid. Okay, so generally, let's see. Yeah, so generally, if you're doing a reaction with two of these molecules, you're gonna end up with a condensation reaction. There's a CH3 here. CH3 is missing. There's gonna be a condensation reaction where this used to be the alpha carbon that attacked the carbonyl, which lost the OET as ethanol. Okay, that's the overall reaction that I've just described in the previous slide. Not very easily understood, but again, you have to practice. You just have to practice. Don't say, I got it. No, you have to practice to see it quickly. So this product right here still have an alpha hydrogen. So it's very reactive to the base and can form another enolate easily. That's why I said after forming your product, the product can go one more step to react with the base. You get a carbanion, which can rearrange to give you an enolate. So we stop that by adding an acid to make sure we always have our product, which is this, stopping any further reactions. So when the alpha hydrogen is taken out by a base, okay, that is after step 1, you might form an enolate, because when this hydrogen is taken out, you're gonna end up with the CH3 is there. I think in the notes it's not showing. You're gonna end up with a carbanion, and this carbanion can do resonances. You use the lone pair, make a double bond, this opens up, you get your enolate. Alternatively, if you use your carbanion, make an enolate on this other side, you're gonna end up with this molecule. So to stop this enolate formation, that's why we add an acid like we did here. The acid will quench the negative charge. You get your stable product that won't form any more enolate. Okay, so the acid is required to destroy the remaining alkoxide and the proton on the beta keto enolate. This is the beta keto enolate. That's why we need the second step to stop this enolization. That's why we need this step to stop the enolization. Okay, the two carbonyl groups are not equivalent. The ketone is more reactive than the ester and can be reduced by sodium borohydride and can react fast to a nucleophile. What does that mean? You see how you have your product. This product, you have both ketone and an ester. So if I am to circle the groups in the product, that looks like a ketone, right? And this is an ester. Ketones are more reactive than esters. Okay, ketones are more reactive than esters. So if you use sodium borohydride in such a reaction, you know sodium borohydride is a mild reducing agent, mild reducing reagent. So this sodium borohydride will only reduce the ketone to the alcohol. okay, but will not touch the ester. It's not strong enough to reduce the ester to an alcohol. If you want both of them to be reduced to alcohols, one will want to use a stronger reducing agent like lithium aluminum hydride. Of course, this will be step 1. Step number 2, you always quench with H3O plus. So use lithium aluminum hydride, which is the main reagent. That's gonna reduce the ketone to the alcohol and the ester to the alcohol. So you get a primary alcohol from the ester, secondary alcohol from the ketone. Of course, the whole arm here will fall off as ethanol, right? This part will fall, actually this part will fall off as ethanol. Using a strong reducing agent. With mild reducing agent, only the ketone reacts, the ester survives. Okay, so what do we mean? We mean if you do your Clancy reaction, okay, I'll keep correcting, you have a CH3 here, you have the what we call beta ketoester. It's beta because you have a ketone on the beta carbon, ketone on beta carbon, beta ketoester, there's an ester here. Only the ketone will be reduced by sodium borohydride, the ester will survive, and then by heating you can lose another alpha hydrogen. Okay, let's say you have a base like water, which will take this out, this makes a double bond. In presence of H plus, this will be protonated, which will fall off as water, similar to what we did with aldol condensation. So you lose water, OH will fall off as water as you make your double bond, so you can get your unsaturated ester. And the double bond there can further be reduced by hydrogenation to get single bond. See, you have 2 hydrogens here, you're gonna end up with 4 of them. So this slide is not here to scare you, it's just giving you an example of how synthesis can proceed in the lab, going from one ester to a longer chained ester. Okay, so moving from here to here, one can follow all these reactions to this point. That's the life of an organic chemist. Not very fun. Okay, so I've shown you the application of Clancy condensation, and we've talked so much on the mechanism. I think this chapter will end here. I will not ask you about the mechanism in the test, maybe small portions in our quiz or Moodle quiz, if any.